So in the last segment, I said that satisfiability is NP-complete thanks to the theorem of Cook and Levin, and showed you one example of a reduction from satisfiability to a somewhat artificial problem called NUS, non-unique satisfiability, and thereby showing that NUS is also NP-complete. In this segment, we're going to take another version of satisfiability which is known to be NP-complete, and it's a little easier to work with in reductions. And this version of satisfiability is called 3-SAT. So basically 3-SAT is a kind of restricted version of satisfiability where you only allow Boolean formulas of a certain form and ask whether those formulas are satisfiable. 3-SAT also happens to be an NP-complete, and we will take that for granted and then show other problems NP-complete. So basically 3-SAT says given a Boolean formula in 3 conjunctive normal form, is it satisfiable? So what's the formula in conjunctive normal form? Conjunction is just a fancy word for the AND operation, denoted like this. The OR operation also has a fancy word. It's called disjunction, but we won't use that here. A formula is in conjunctive normal form when it's the AND of many things. So the top level thing that's happening in the formula is AND. So if you look at this formula, everything at the outermost layer is ANDs. Conjunctive normal form if it's an AND of M clauses, where each clause is an OR of some number of variables and their complements. So, for example, this is a clause which is the OR of 4 different variables and their complements. The name for these things, like these things, are called literals. Literals is just a fancy way of saying either a variable in original form or a variable in complemented form. So complemented meaning with a not before it. So a clause is an OR of literals. A conjunctive normal form formula is an AND of clauses. So this is a CNF, conjunctive normal form. And a formula is in 3 CNF when each clause has at most 3 literals. There's a variant of definition which says a formula is in 3 CNF if each clause has exactly 3 literals. And we will use the at most definition here. So a formula is in 3 CNF if every clause has at most 3 literals. Here's an example of a formula that's in 3 CNF. As you can see, there are 2 clauses. The first clause has 2 literals, and the second clause has 3 literals. And the CNF problem asks, the 3-SAT problem asks, given a formula in this form, is there an assignment to the Boolean variables that causes the whole formula to evaluate to true or 1? But omitting the details, as I said earlier, it can be shown that satisfiability can be reduced to 3-SAT in polynomial time. And 3-SAT is clearly in NP. Someone gives you an assignment, you can check that it satisfies the formula. And therefore, 3-SAT is NP-complete. So let's take that for granted now and give an example of a non-trivial reduction showing a completely different looking problem is NP-complete as well. And this problem is going to be the independent set problem, which is much like the clique problem. I just chose independent set because the picture we draw is nicer for this problem. So an independent set in a graph is a set of vertices, no 2 of which are adjacent. Okay, so here is the graph, and the 6 vertices 1 through 6 are independent because there's no edge between any pair of them. So this is an independent set. And the independent set decision problem, ISDP, is given a graph G and an integer k, does G have an independent set of size k? So if you're given this graph here, in this example, if you're given this graph in the picture, and you're given k equal to 6, the answer is yes, because of this orange vertices that are shown here. If someone showed you these orange vertices, you could count them up and say, oh, there are 6 of them. You could check that there are no edges between any pair of them and be convinced that this graph has an independent set of size 6. So this is a problem in NP, because given a solution, the 6 vertices, you can verify that it is indeed a solution that satisfies the requirements. Now we're going to show that independent set is NP-complete. The decision problem is NP-complete by showing a polynomial time reduction from 3-SAT to independent set. And maybe it's time to highlight the direction of this reduction. 3SAT is a problem that's known to be NP-complete. Independent set is the problem that we would like to show is NP-complete. You reduce from the known hard problem to the problem you want to show to be hard. Because if you do this, then you are proving that independent set could not have a polynomial time algorithm. So basically, let's think a little bit about the reduction. What do we start with? What's the input? The input is an input for SAT, and the reduction should output an input for the independent set problem. So it starts with a formula in 3CNF form and produces an input for independent set. And what's the form of an input for independent set? A graph and a number k. That's what an input, the independent set decision problem needs as input. So if you're given this formula as an example, x and so on, how do you produce this graph and how do you produce the number k? So let's be given a formula phi. I'm going to do this example while also talking about what happens in general on the right-hand side. So you're given a formula phi with n variables and m clauses. And look at this example too to follow along. We're going to create a vertex for each occurrence of each literal. And I'm going to group these vertices in this way. So this is all the vertices that occur in clause number 1, which is right here. This is all the literals that occur in clause number 2, which is the one right here. All the literals that occur in clause number 3, and all the literals that occur in clause number 4. And this is what we're going to do in general. We're going to create m groups of vertices, one corresponding to one for each, one for the literals in each clause. Okay. Now we will join every pair of literals from the same clause by an edge. So we just, in this case, there are 3 vertices in this clause. We'll draw a triangle. If there are two literals in this clause, we just draw an edge. If there's one literal, of course, we don't do anything. What does this do? This ensures that in any independent set, you can choose at most one vertex from any group, because all pairs of vertices in a group are adjacent, and so you couldn't actually choose 2 vertices from the same group. And finally, we also add the following edges. Between any vertex representing x anywhere in the graph, we draw an edge to any vertex representing x bar anywhere in the graph. So x bar occurs this one place, x occurs in 2 places, and we drew these two, this edge here between x and x bar, and this edge between x and x bar as well. So any pair of vertices that represent sort of conflicting or contradictory literals, one is a negation of the other, you draw an edge between. Okay? And that's the graph. So you create a graph from the formula in this manner. So again, recall that we're going to take an input for 3SAT and produce an input for independent set. Well, there's one more piece to the input for independent set. What's that? You need to specify the number k. You want an independent set of a size k. What is that k you want to specify? We're going to specify k to be m, the number of clauses in the original formula. So m is the number of clauses in the original formula. And we're going to require the independent set to have k vertices. That is the number of clauses vertices. That's the reduction. So now, how do we show that this reduction is correct? You have to do 2 things in order to prove that a reduction is correct. First of all, you have to prove that reduction runs in polynomial time. That's the third thing. And that's easy to see because I just described to you how this reduction is done. And you could imagine writing a program to do this, and it should be a pretty fast program. So there are 2 things you have to do to prove a reduction is correct. One is to show that if this formula is satisfiable, in general, if the formula phi you're given is satisfiable, then the graph you produce as a result of the reduction is going to have an independent set of size k, which is m. And the flip side is, if the graph you produce has an independent set of size m, then the original formula is satisfiable. So those are the 2 things you have to show. So let's look at the first part. If phi is satisfiable, why does the graph have an independent set? What does it mean for a formula in conjunctive normal form to be satisfiable? Recall again the form of the conjunctive normal form. It's an and of clauses where each clause is an or of literal. So you have some literal or some literal or some literal, or some literal, an or. Okay, so you have these 3 literals. and then you have an and of such you have an and of such clauses, an and of such clauses like this. There might be many of them. What does it mean for such a formula to be satisfiable? Well, because you have an and relating all the clauses, each of the clauses must evaluate to true. If any clause evaluates to false, the whole formula is unsatisfiable, because ands have that property. The only way that an and of many things is going to be true or 1 is if each of the things is 1. So each clause has to be satisfiable. That means that the assignment must make at least one literal true in every clause. Because if you make all the literals in a clause false, then the or of all false things is also false. If you make at least one literal true, the clause will be true and everything is good. So any satisfying assignment has this very simple form. It makes at least one literal true in every clause. Okay, so that's the characterization of satisfying assignments for CNF, conjunctive normal form formulas. So if phi is satisfiable, then using the satisfying assignment, we can pick one literal from each clause that evaluates to true. I just argued why. Now, if you look at all the literals that are true in different clauses simultaneously, you cannot have x be true in one clause and not x be true in another clause, because only one of x and not x is true. So the literals that are making each clause true, none of them are negations of each other, and they all sit in different clauses. So look at the way we constructed the graph. No two of the vertices corresponding to these literals will be joined by an edge. So these vertices form an independent set in the graph, and since we picked one vertex out of every clause, the size of this independent set is the number of clauses m. So this means if the formula is satisfiable, we've just shown that the graph has an independent set of size m, which means that the graph is a graph with the number k equal to m is a yes example of the independent set problem. So we've shown that if the answer is yes to the input for satisfiability, the answer is yes to the input we created for independent set as well. That's one direction. The other direction is you can prove it in one of two ways. These are logically equivalent. One is to show if the answer is no to the input for satisfiability, the resulting graph will not have an independent set of size k. Or another way to prove it is if the graph we create has an independent set of size m, then the original formula is satisfiable. Okay? So if G has an independent set of size m, then we must pick one vertex from each clause. Recall that we joined all the vertices corresponding to one clause. So we cannot pick two vertices from any clause. So we can pick at most one vertex from each clause, but we need to pick m vertices, and there are only m clauses. So we have to pick one vertex from each clause. And also, all the vertices we pick, no two of them can be negations, can correspond to literals that are negations of each other, because they would not be independent. There would be an edge between them. We are guaranteed that the independent set corresponds to literals, one from each clause, such that no two are negations of each other. Now, if you so you can make all these literals true, because there are no negations in this set of literals. If you make all these literals true, you've made one literal true in every clause in the original formula, and therefore you've shown that the formula is satisfiable. So if the graph we create does have an independent set of size m, then the original formula is satisfiable. That means that this proves that the independent set decision problem is NP complete. And this is just one example, and one of the simpler examples of reductions. There's a lot of clever reductions showing literally tens of thousands of problems NP complete by now. All kinds of problems. Every problem I mentioned earlier in a previous segment, the Hamilton cycle problem, the partition problem of dividing numbers into two sets that add up to equal values, the problem of coloring a graph with three colors, all these problems are known to be NP complete. And these are just the tip of the iceberg. There's basically many, many, many problems that arise in practice that we would love to be able to solve efficiently, which are unfortunately NP complete. It's good to know that a problem that you want to solve is NP-complete for at least one reason. You stop wasting time trying to find an efficient algorithm for that problem because it's likely that there is no such algorithm. Of course, if you find an algorithm, it would be a major breakthrough, the biggest breakthrough in computer science, as I said. But more likely, this problem does not have an efficient algorithm. Currently, we do not know if this class P of efficiently solvable problems is equal to the class NP of efficiently verifiable problems. Of course, we do know that NP is at least as big as P. Everything in P is definitely in NP. So we can say that. Why can we say that? Because if a problem is in P, you don't even need to be given a solution. You can just verify that the answer is yes, because you can compute the answer for yourself efficiently. We have tens of thousands of NP-complete problems. If any one of them is solved in polynomial time, then P equal to NP. And every problem in NP can be solved efficiently. So there are some practical implications, and let me wander off into something a little bit less mathematical and a little bit more fun to give you an idea of what this all means. So one implication, if P equal to NP, is that if a mathematical theorem has a short proof, and of course proofs can be verified rather easily, right? Because that's the idea of proofs, that if some mathematician or logician reading a proof can tell if it's valid or not. They can check every step of the way and ensure that the proof is correct. So proofs are things that are in NP. But if P equal to NP, anything in NP can be solved in polynomial time. So that means that anything that has a proof, the proof can be found efficiently. It has a short proof, can be found efficiently. So a little bit more out on a limb, less mathematical, less formally, you could say that appreciating beautiful music, for example, is the problem of verifying, if you like, auditorily verifying that a piece of music is good. So appreciating beautiful music is a verification problem, and that's in polynomials. So most people can appreciate beautiful music or whatever they define to be beautiful music. So the problem of verification of music is in polynomial time. But the problem of coming up with beautiful music, that's coming up with a solution that someone can verify, that's in NP, because if someone gave you the beautiful music, you could appreciate it, but you don't know how to compose the music yourself, or at least it's not everyone can do it. But if P equal to NP, and this is completely meant to be only an analogy, not a real statement, if P equal to NP, what that means is that music appreciation is just as easy as music creation. So we can all be creators of music just because we know how to appreciate music. And you can replace music with art, and the same thing is true. Anyone can be a great painter if you only know how to appreciate beautiful paintings. Because P equal to NP just says that creativity can be automated. That's the sort of punchline summary of what P equal to NP means. Creativity is basically the power of an NP algorithm to come up with these solutions out of nowhere. Just the verification, appreciation is just the power of a polynomial time algorithm to verify that something is beautiful or something is correct or something like that. And if P equal to NP, there's no difference between creativity and just the verification part. So creativity can be done automatically by machines. We don't need musicians and composers and artists. We can just let computers produce all the beautiful music and art we want. But more technically, let's talk about this course and summarize it now. So what did we learn in this course? We learned a lot about data structures, how to organize data in order to be able to access data for particular purposes or with particular operations. We learned some important algorithm design techniques, sort of the inductive way of designing algorithms incrementally in the beginning, divide and conquer, dynamic programming, and greedy algorithms. And we learned in the end that not all problems have efficient algorithms. Even problems that are important in practice, some of them may not have efficient algorithms at all. So when confronted with a problem, what should you do? Well, you now have a toolkit of techniques for solving it, designing algorithms for it. So try to see if any of the techniques you learn will lead to an efficient solution. If they don't, perhaps the problem is too hard. although you haven't had too much practice with this, one thing that one can try to do is to show that the problem is NP complete. And that says avoid wasting your time looking for an efficient algorithm. That probably doesn't exist. There are many further questions that we haven't been able to cover in this course. So one thing is we focused on the running time of algorithms as the only object of interest. In fact, one thing that's almost as important as time is the amount of memory or storage that's needed by an algorithm. And sometimes algorithms are limited not by their running time, but by the amount of storage that they need. So there's a whole study of algorithm analysis concentrating on how much space an algorithm uses. We didn't touch that, but there is a lot to be done there. Another question that we haven't touched on is what do we do if we know a problem is NP complete? There is seemingly no efficient algorithm for the problem. There are problems that are even harder than NP complete, and problems for which we definitely don't have efficient algorithms. Well, one thing we can try to do, of course, is to take a practical approach, design an algorithm that seems to work well generally, even though in the worst case it might not. These are called heuristic solutions. So try to come up with heuristics that work well to solve the practical instances that you have to solve. Another thing that people have worked on a lot is instead of solving these optimization problems exactly, not the decision problems, but the optimization problems exactly, you can try to come up with an approximate algorithm that will produce a guaranteed approximation. That is, maybe a solution that's no worse than 10% worse than the optimum, something like that. So there are certain problems that are hard to find the exact best answer to, but you can come within 10% provably. So there are algorithms that do that. We haven't touched upon these. There are many other algorithm designs and design techniques and heuristic approaches that I haven't talked about in this course. You've only seen the basic ones. And as we deal with the big data explosion and as we deal with different models of computing, cloud computing, computing with multiple computers, we have different algorithms that work better in different models of computation. In this course, we've only focused on the model of sequential computation, where basically one computer is computing everything in a sequential manner. There's a lot more work that happens in algorithms on other models of computation, and if you study further, you can explore all of these further direction.